Hello, my name is Rui Cardoso. I'm Senior Lecturer at Brunel University London, UK, and I'm going to deliver a short course on numerical methods for structural analysis. We will start with the weighted residuals, and then the final goal is to get into the finite element method, which is the most common used method in structural analysis. Before I start, I would like to give this information. So I recently published this book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. This book includes, so it is a 700 pages book. It includes many introductory chapters, but the chapters we are going to focus in this short course is going to be numerical methods, basically this chapter 10 and also chapter 11. So like I said, we will start with the weighted residuals method. Okay, we'll talk about Galerkin's method, collocation method, and then we will move to weak formulations, which is very important to derive the finite element matrices for elasticity. And then we will, in this section 10.4, we will derive some important formulations for some specific elements, for 1D elements, 2D and 3D elements. In chapter 11, we'll focus more on plate and shell elements. Okay? So in this short course, so these are some figures I took from my book. So you will be able to model this kind of structural components. For example, an hinge. Okay. So you have MATLAB scripts to get the finite element matrices for the 3D elements, brick elements. That is included in the book. So you can predict the equivalent von Mises stress. So the pin here is modeled as a rigid body, but then the other two parts of the hinge, they are deformable bodies, and you can see the distribution of the von Mises stress. You can also see the distribution of displacements or wherever else you want to see. Also in the book, in the chapter for plates and shells, you will you have basically the MATLAB routines to build the shell elements, and if you want to implement that in your MATLAB code, you can get results similar with these ones. For example, this one with a cylindrical shell with a concentrated force, so you get the deforming configuration, something like this. So this is something you can predict with the MATLAB scripts in the book. So another type of things you can do from the book is a buckling analysis, getting the buckling modes for a plate element, in this case with some symmetric boundary conditions. You can get different buckling modes and predict the structural behavior of these structural elements under compressive or in-plane shear loading. Okay. So what we are going to learn in this short course is basically the weighted residuals and finite element method. So with the weighted residuals is the foundation to get the finite elements that allow to do this kind of problems, analysis of this kind of problems. So I hope this short course is valuable to you. So yeah, that's it. Hello everybody. So let's continue our course on numerical methods. Today what I would like to do with you is to continue the example from our last session, but to introduce the weak formulations. So we are going to do the same example of the beam with a distributed uniform load of 10 kilonewtons per meter. So I'm not going to repeat again the same beam, but what I'm going to write here is the weighted residual that we achieved in our last session. So we found out that the weighted residual was the integral in the domain which is from 0 to 1. So the domain is in the x direction of the beam, the longitudinal direction of the beam. And we have the weighting functions, W. So the subscript 2, as if you remember, it means that we are considering two terms in the approximation functions. And our residual, you can check in the previous session, was given by this equation here. EI is the flexural stiffness of the beam, second derivative of the deflection, plus 5x squared minus 5x, right? So this was the weighted residual which we wanted to minimize, make it equal to 0. So this was the residual, R2, okay? We want to minimize this residual, so we affect this residual with a weighting function, this weighting function here, which if you use the Galerkin method, this weighting function, so this is a very quick review, this weighting function is going to be equal to the shape functions, right, for Galerkin's. I can write here Galerkin's method. And then in the last session, we solved this equation and we obtained so I don't know if you remember our approximation function. I can write here as well. Our approximation function was given by two terms. So this was our first shape function, phi1, if you want, multiply an unknown coefficient a1, and then the second shape function that we defined was this one here, okay, that multiply our second coefficient. So this is a very quick summary of what we did in the last section, and what I propose to do now is to solve this same example, but before that we will apply a mathematical manipulation. So we are going to integrate by parts, okay, and that will give rise to what is called weak formulation. And this weak formulation can be interpreted in some different ways, but in this context, the weak comes from by the fact that integrating this equation by parts, we are going to reduce this. Here we have a second derivative. We are going to avoid having a second derivative. So when you integrate by parts, and we are going to see that quite soon, you are going to see that I will reduce this residual from a second derivative to only a first derivative. Okay, so that is a great advantage for finite element analysis, as we are going to see later. Not today, but in a different section later, okay? Okay, so I'm going to integrate now this weighted residual by parts, okay? So this integral I'm going to integrate by parts. And before doing that, I did some transformation here. As you can see, this corresponds to this first term, this integral, and I'm separating. Now this integral here corresponds to W2 times this here, right? You can see, so I didn't do anything special. Now, yes, what I'm going to do now is integrate by parts. So, and I'm going to integrate by parts only this integral here, because this one here is not necessary. I don't have any derivative here, so I don't need to integrate this one by parts. Okay? So, integrating this first one by parts means I have this integral in the domain, So as you can see here, this step from here to here, what happened was I don't have this second derivative anymore, so it was transformed into this first derivative. And then the weighting function here, now here I'm going to have the derivative of the weighting function. Okay? So this comes from the from the integration by parts. Of course, this is not enough. So in integration by parts, I also need to add the terms on the boundaries of my domain for x equal to 0 and x equal to 1, which is the boundaries of my beam, where I have the supports. And the terms I need to have is, so I keep the first derivative and need to multiply by the weighting function. So I don't do here the derivative of my weighting function at the boundaries. And then I need to evaluate this at both boundaries, or at both supports for x equal to 0 and x equal to 1. So that's why these two terms appear here, okay? And this last integral basically is just this one here, so I didn't change anything. I'm just reproducing the same integral there. Right, so what you have here now is these two terms at the boundaries. They are going to be equal to 0, and the reason is, if you are using the Galerkin's method, for the Galerkin's method, the weight function is going to be replaced by the shape functions, remember? So this is for Galerkin's method, okay? And if you evaluate then the shape functions at x equal to 0 and x equal to 1, you can clearly see, so if we go back here, so the shape functions, they are here. So this is shape function number 1, shape function number 2. If you evaluate, for example, shape function number 1 at x equal to 0 and x equal to 1, you can see that clearly that shape function phi1 is going to be 0 at both boundaries, both supports, and same happens for the shape function phi2. When you replace x by 0 and x by 1, it is also going to be equal to 0. That is the reason why these two terms here, when after integrating by parts, they become equal to 0. And that is one important aspect, and which is related with the selection of the shape functions for the problem. Like I said in the last session, we have chosen the shape functions so that they fulfill completely the boundary conditions, which was deflection for x equal to 0 and x equal to 1, the deflection at those 2 points equal to 0, right? So the shape functions, they were chosen so that these two boundary conditions are met. And that, of course, is now reflected on this integration by parts with the elimination of these two components of the integration by parts. So this is going basically to be the weighted residual that we are going to work. That is the result of the integration by parts. And you can see here that you don't have anymore any second derivative as you had here in this original weighted residual here. You can see clearly here a second derivative of your approximation function, while after integrating by parts, you don't have a second derivative anymore. You have the product of two first derivatives, okay? That is quite an important thing, especially for finite element analysis, as we are going to see, not today, but in a forthcoming session in the future, okay? All right, so next step now is to use Galerkin's method. So this is approximation function, which we defined in the last session. This is the first derivative of the approximation function because we need the first derivative here, right? And these two terms, so basically we need to have the derivative of the first weighting function in order to x, and we need to have the derivative of the second weighting function in order to x, but because we are using Galerkin's method, the weighting function is replaced with the shape function. Okay? And the derivatives of the shape function are quite easy to do. So this is shape function number 1. This is shape function number 2. And these are the derivative of the first shape function, and this is the derivative of the second shape function. And they are here, right? So the only thing I have to do now is to replace all of these in the weighted residuals I have here after integrating by parts. That's what I did. Sorry, this is already written because there was a problem when I did this video. For some reason it was not recorded. So I'm doing is on top of what I did already. So I don't want to write this everything again, so I'm just going through the equations I've written before, okay? Sorry for that. But anyway, so this is, like I said, the weighted residual after integration by parts. Now, after replacing these derivatives and the weighting function, which in the case of Galerkin's is same as the shape functions, and of course, assuming EI equal to 1, like we did in the previous session, just to simplify the calculations. So we obtain, so this is the first derivative, this is the derivative of the first shape function. This is the derivative of my approximation function, dv2 dx. This is my shape function, phi1. If you want, I can put like this. This is the derivative of phi1 in order to x. This is dv2 dx, right? So when I replace here the first shape function, I get my first equation. The second equation I obtain when I replace the weighting function with my second shape function. That's what I did here. So if you want, this is the derivative of phi2 in order to x. This is phi2. This is exactly the same derivative of the approximation function. And then I get my second equation, okay? And you can see now that after solving the integrals in these two equations, or after calculating the primitives, and they are quite basic primitives, I will have two equations for two unknowns, which are A1 and A2. If I do that, I get this result. Okay? A2 equal to 0, A1, 1 over 2. And if I replace these constants in my approximation function, this is the approximation function I obtain. Okay? So my next step was then to compare with the previous results from last session. So remember we did this example for this beam. We calculated the results at the midpoint for x equal to 0.5 for the deflection. The analytical result was minus 0.130 to 1. The Galerkin was minus 0.125, and the collocation method we also did in the last session. The result was minus 0.11719. And now replacing this equation x by 0.5 here and here, that's what I did here. The result you get is minus 0.125. Okay, this is the result after using the weak formulation. And you can see that it matches the Galerkin result Okay, that is one important thing. So the weak formulation result is equal or even better in some examples is even better than the Galerkin's result without integrating by parts or without using the weak formulation. The other advantage of weak formulation is that no need for a second derivative in this example, right? So the integration by parts always reduces the order of the derivative, okay? If you have a third derivative, when you integrate by parts, your problem will be reduced to a second derivative. If you have a second derivative in your integral, after integrating by parts, you have only the first derivative. And that makes a huge difference in the finite element method, as we are going to see later, okay? So this was my quick introduction to the weak formulations. You can obtain weak formulations different methods from energy methods, but this one was just by integrating by parts. And in the next session, we are going to see how we can apply the weak formulation to derive the required equations for the theory of elasticity, okay? This is going to be quite critical because that will allow us to formulate the finite element method for the analysis of structures, for plane stress problems, plane strain, plates, shells, any problem that is, any structural problem you want to do using the finite element method. So these two sessions, the one I did on the weighted residuals and this one for the weak formulation, they were all based on a very simple example of a beam, but they are quite important for the understanding of the finite element method, of numerical methods in general, how they work. So that's why I decided to do in this way, taking one example and explain all different methods for that same example. So I hope you enjoyed and see you soon on the next session. Bye, thanks.